Hello everyone, myself Michael Ravina, Associate Professor, Department of Computer Science and Engineering. The subject is CS 3551 Distributed Computing. The unit is Distributed Mutex and Deadlock. In this video, we are going to discuss about Ricart-Agrawala algorithm and Maekawa algorithm and Suzuki Kasami broadcast algorithm. Ricart-Agrawala algorithm. The Ricart-Agrawala algorithm assumes the communication channels are FIFO. The algorithm uses two types of messages. First one is request and the second one is reply. A process sends a request message to all other processes to request their permission to enter the critical section. A process sends a reply message to a process to give its permission to that process. Processes use Lambert-style logical clock to assign a timestamp to critical section request, and timestamps are used to decide the priority of the request. Each process PI maintains a request defer array, that is RDI, the size of which is the same as the number of processes in the system. Initially, for all I, for all j, RD of that means the request deferred array is 0. Whenever PI defer the request sent by the PJ, it sets RDI of j equal to 1. After it has sent a reply message to PI, it sets again RDI of j equal to 0. The description of the Ricart algorithm. In this algorithm, these are the steps. First step is the requesting the critical section. When a site SJ wants enter to the critical section, it broadcasts a timestamp request message to all other sites. When the site SJ receives a request message from the site SA, it sends a reply message to the site. If site SA is neither requesting nor executing the CS, or if the site SJ requesting and SI's request timestamp is smaller than the site SJ's own request timestamp, otherwise the reply is deferred and SJ sets RDJ of j equal to 1. This is the first part. Then second part is executing the critical section. The site SA enters the critical section. After it has received a reply message from the every site, it sends a request message too. Then final step is releasing the critical section. When the site SA exits the critical section, it sends the deferred reply messages for all j. If RDI of j equal to 1, then send a reply message to SJ and set RDI of I of j equal to 0. When a site receives a message, it updates its clock using the timestamp in the message. When a site takes up a request for the critical section for processing, it updates its local clock and assigns a timestamp to the request. Correctness of algorithm. The algorithm proved by using the theorem, that is the Ricart-Agrawala algorithm achieves mutual exclusion. The proof is by contradiction. Suppose there are two sites that executing the critical sections concurrently. The first site request has higher priority than the request of another site. Then the clearly SI receives the particular SJ's request after it had made its own request. Thus, SJ can concurrently execute the critical section with SI only if SI returns a reply message to SJ before the SI exits the critical section. However, this is impossible because SJ's request has the lower priority. Therefore, the Ricart algorithm achieves mutual exclusion. The performance of the particular algorithm requires n-1 request message and n-1 reply messages. So, it requires 2 into n-1 messages per critical section. So, the synchronization delays in the algorithm is T. The next one is the Maekawa algorithm. The Maekawa algorithm was the first quorum based algorithm mutual exclusion algorithm. The request sets for sites in Maekawa algorithm are constructed to satisfy the following condition. Then there are 4 conditions: M1, M2, M3. These are the some of the conditions. Using this condition, Maekawa used the theory of projective plans and showed that n equal to k into k minus 1 plus 1. This relation gives a modulus of Ri equal to n. The conditions M1 and M2 are necessary for correctness, whereas the condition M3 and M4 provide the other desirable features to this algorithm. Condition M3 states that the size of the request of all the sites must be equal, implying that all sites should have the equal amount of work to invoke the particular mutual exclusion. Condition M4 enforces that exactly the same number of sites should request permission from any site, implying that all sites having equal responsibility in granting permission to other sites. The algorithm has also three steps. First step is requesting the critical section. Second is executing a critical section. Same procedures. First one is the first step is requesting critical section. A site SJ request access to the particular critical section by sending the request message to all the sites in the request set Ri. When a site SJ receives the request message, it sends a reply message to the particular SI. Provided it has not sent a reply message to a site, hence it recipient of the last release message. Otherwise, it queues up the request of I for later consideration. Then second step is the executing the critical section. In this executing the critical section part, the site SA execute the critical section only after it has received the reply message from every site in Ri. Then final one is releasing the critical section. After the execution of the critical section is over, the site sends a release message to every site in the Ri. When a site SJ receives a particular release of message from the site SA, it sends a reply message to the next site waiting in the queue and delete that entry from the queue. If the queue is empty, then the site updates its state to reflect that it has not sent to out any reply messages since it received of the last release message. Handling deadlock. The Maekawa algorithm handles deadlock by requiring a site to yield of a lock. If the timestamp of the particular request is larger than the timestamp of some other request, then waiting for the same lock. A site suspects a suppose deadlock means whenever a higher priority arrives, it waits at a site because the site has a reply message to the lower priority request. Deadlock handling requires 3 types of messages. First one is failed, then second one is inquire, then third one is the yield. Failed message from site I to SJ that indicates SI cannot grant SJ's request because it has currently granted permission to a site with a higher priority request. Inquire means an inquire message from SI to SJ indicates that SI would like to find out the SJ. It has succeeded in locking all the sites in its request set. Yield means a yield of message from its SI to SJ indicates that SI is returning the permission to SJ. Then next one is the Suzuki Kasami broadcast algorithm. If a site want to enter the critical section and it does not have the token, it broadcasts a request message for the token to all sites. A site which possesses the particular token, it sends the requesting site upon the receipt of the particular request message. If the site receives the request message when it executing the particular critical section, it sends the token only after it has completed the execution of the critical section. The algorithm must efficiently address the 2 design issues. First one is how to distinguish an outdated request message from a current request message. Then second one is how to determine which has an outstanding request for the critical section. These 2 design issues are overcome by using this algorithm. The algorithm has three steps. First one is requesting the critical section, then second one is executing the critical section, then after one is releasing the critical section. That means requesting means if the requesting site SA does not have the token, it then increments its sequence number, that is Rn of I, and sends a request of I, Sn message to all other sites. When a site Sj receives this message, it sets the Rn of J to maximum of Rn of I, Sn. Then Sj has an idle token, then it sends the token to the particular SA. If Rn of I equal to ln of I plus 1. Executing the critical section. The site SA execute the CS after it has received the token. Then next one is the releasing the critical section. Having finished the execution of critical section, the site SA takes the following action. First, it sets the ln of I element of the token array equal to Rn of I. Then next, for every site Sj whose ID is not in the token queue, it appends its ID to the token queue. That means Rn of I equal to, if Rn of j equal to ln of j plus 1. If the token queue is non-empty, after the above update, SI deletes the stop site ID from the token queue and sends the token to the site indicated by the ID. Correctness of this algorithm is proved by using the theorem. The theorem is that a requesting site enters the CS in the finite time. Here the proof is taken by token request message of a site, that SA reach all the site in the finite time. Then since one of these site will have token in finite time, then the site SI's request will be placed in the token in the queue in the finite time. Since there can be at most n-1 request in front of this request in the token queue, so the site will get the token and execute the CS in its finite time. Performance: no message is needed and the synchronization delay is 0 if a site holds the idle token at the time of its request. If a site not hold the token when it makes a request, the algorithm requires n messages to obtain the token. Synchronization delay in the algorithm is 0 or t.